Today we are going to see the solution for Advent of Code day 20. I can definitely see that Christmas is in the air. And finally, after a few days of absolute nightmares, we have a reasonable, enjoyable problem. And this problem also let me explain a couple of interesting 42 features. So I start defining a point class, and this point class of course have two fields, x and y, and I define three very similar methods, plus, max, and min, where they take 2 points, but they have some different way to combine them. So of course the plus will get the sum of the x and y coordinate, the max will get the maximum of the x and y coordinate, and the min will get the minimum. However, I've done those three methods in three different ways, so that we can explore different ways to write those kind of methods in 42. So let's see, the first one, the plus, as you can see here, is just making a new point, and is making that the x is just this.x plus that.x, and the y is this.y plus that.y. Notice how we don't need to repeat the type point, because that's the expected type in the situation. So we can simply use the slash. The second method we show is the max, and this is the most explicit way to write that method. So we first extract the x and the y coordinate from this, then we extract the x and the y coordinate from that, and now that we have our four numbers, we can just create a new point, and again we are going for an explicit style, so we write point explicitly instead of using the slash. X equal x0 dot max x1 and y equal y0 dot max y1. For the minimum instead, I'm using the withers. Withers allows us to take an object and create a similar object that is all the same except for the value of a specific field. So we can call the wither twice in order to get an update on the x and an update on the y. So we can do this.width, x equal the current x minimum that.x, and then dot with y, the current y minimum that.y. Notice how we have to use an explicit type annotation to convince the system that the wither returns a point. The withers are created for our convenience by data. Thus, they are not explicitly declared in the code right now, and so the type system needs a little bit of support to figure out what's the return type of the width. We then make a map data type that mostly wraps an hash map that will go from points to booleans, but we will also add a few more fields to represent the problem domain better. In particular, we are representing an infinite map, and the idea is that there will be a default value for everything that is not in the map, and we are going to call this outer because the idea is that this is the value of everything outside, far away. We then have two extra fields, top left and bottom right, to record the rectangle that is currently, let's say, active in our map. You know, the rectangle where there are values that are explicitly inserted in the map. To implement the put method, we delegate on the put method on the map, but we also update the top left and the bottom right so that they keep recording the minimum and the maximum point as inserted in the map. To conveniently extract values from our map, we just have a method val that delegates on the map val, but in case there is no value in the map, we just return this.outer. Finally, the puzzle is asking us for all the points in the map to look in the points around and to use the boolean 0, 1 to create a boolean encoding that represents the value of the neighborhood. The whole method body can just be an int accumulation, so we can start from 0, do .acc, and then make a block that will slowly add numbers to our value until we get the right boolean encoding. To explore the neighborhood of a point in 42, I think the best way is to use the range function and go from -1 to +2. That is, we want to go to -1, that is one step before our point, and then explore -1, 0, and 1. And so in this way we stop at 2, because as usual, ranges goes from the first value included to the second value excluded. In the body of our for, we will make a point with xy and yy, and we will compose it to our current point in order to locate all the points in the neighborhood. And for all of those points, if the map is lit up in that point, we just add a carefully computed number to our accumulation. Since we start from the most significant bits, we will have our special number start very big, and we will divide it by 2 every time. So the first time we will add 258, then 124, then 64, and so on. Finally, the step method, where we will take all of the things that we have built and put together the main solution for this puzzle. The main idea is that this algorithm is looking to the points in the state 1 and creates the value for the state 2. So if we were to try to mutate the map while we perform the algorithm, we will lose the information that we need to progress. So the first step of our algorithm is to create a new map, and then we will populate it by exploring the old map. We extract the coordinate from the top left and the bottom right, and then we look to all the points in our range plus 1. So we basically grow our range of 1 step on both the negative and the positive direction. In this way, we can explore not just the explicit point on the map, but also all the points of the outer border. Those points have one of the explicitly inserted points in their neighborhood. To make this double for, we make the range start from x0 minus 1, so we explore 1 extra point, and then we go to x1 plus 2. So, why plus 2? Well, you will think to put a plus 1 there in order to extend by 1. But remember, the range always go from the first one included to the second one excluded. And our points are the real border. So there was an actual point that had x1 as a coordinate. So in order to visit that one, we need to add plus 1. We also want to get 1 extra, and so we add plus 2. In the body of the for all the x's and y, we make the point in x and y, and we check the binary encoding of the 3x3 neighbor of this point. The x in 42 is like an assertion in most languages, and so this gives me a good confidence that my binary conversion is correct. We then update the new map with the newly found value for that pixel. Finally, we need to update the default value, the value for all the pixels that are very far away. In this puzzle, to change the default, we just have to look to the current default. If it's true, we need to return the rightmost key value, and if it's false, we need to return the leftmost key value. For my puzzle input, since it started with a hash and ended with a dot, it will mean that every round I will go off, on, off, on, off, on, and so on. The key class is just a collection of bools. In 42, you can define collections with the name you want. So when I originally wrote the code, I thought that key was a great name to represent this conversion algorithm, because it's sort of like an encoding. But looking at it right now, maybe it wasn't the best choice of a name. In the main, we first read the input by creating an object capability, passing the file name, and then we split on the input to make the key and the map. Oh yeah, it's a tempest day here in Wellington, so you may be feeling a lot of wind in the background. To make our key, that is just a list of bool, it's very easy. We just make an empty key, and then for all the I in input.split, we add the result of the check. Is our current character that we just read and hash or not? For the map, it's similar. We first create our empty map, and then for all the lines in our input and for all the characters in our lines, we will put a new element in the map. We also want to know the index of the current line and the current character in the line, and so we can just make our for iterates on both the line and the index in the line, and on the character and the index in the character. In the point in position LI/CI, we add the result of checking if the current character is actually equal to hash. And that's it, that's completely filling our map. You maybe notice a little bit of an inconsistency here. In line 56, to create our list of booleans, we use the power of the slash, and we add the elements to the list that we are creating. While for the map, we are just using the map by name. Both styles are possible in 42, but to enable the slash on the map, I will need to add an extra method to the map. Finally, for 2 steps for part 1 or for 50 steps for part 2, we compute the step of the map. And since we create a new map every time, we will have a step operation that returns a new map, and we will update the map local variable. Finally, we need to count how many truths there are in our map. And we can use another int accumulator, and this time we use the addIf method that adds 1 if you pass a boolean true or 0 otherwise. Notice how this problem is only well defined if we stop in a moment where the outer amount of the map is off. Otherwise there will be an infinite amount of light up points. So this is all for Advent of Code day 20. See you next time, probably for the next chapter of the tutorial. This is going to expand on collections and how the slash really help us to write compact code that look a lot like Java streams, but without any lambda.